The internet glance is so far away that it is catching light that has already been traveling for more than 13 billion years. The universe has been expanding, and thus the light has been stretching along with it. The majority of distant worlds we recall are close to the time of the Big Bang. The vastness of the universe might appear overwhelming, but it began in its entirety from what we allude to as the singularity. As of now, this is how we apply the Big Bang Theory's interpretation. Nevertheless, the James Webb Space Telescope, JWST, has shed light on significant mysteries regarding the beginning and growth of the universe, leaving us speechless. The renowned physicist Brian Cox has proclaimed that the noteworthy discoveries made by the JWST might actually reshape our understanding of the entire universe. Join us as we delve into these brand new discoveries about the heavens that promise to alter our understanding. The James Webb Space Telescope, named after the well-known NASA executive James E. Webb, is still a wonder in ongoing galactic investigation. This telescope represents a huge mechanical advancement from its predecessor, the Hubble Space Telescope. Thanks to a collaboration between the American Space Agency NASA and the Canadian Space Agency, the JWST surpasses the capabilities of its herald. It employs cutting-edge design and technology optimized for focusing on the universe in incredibly fine detail. Like the Hubble, the JWST conveys sharp images of heavenly bodies, but it primarily operates in the infrared range. This interesting component permits it to penetrate astronomical debris and capture celestial objects that were previously hidden from our view. With its enormous 6.5-meter primary mirror composed of 18 hexagonal segments, the JWST greatly exceeds Hubble's reflector. Positioned approximately 1.5 million kilometers away from Earth, it orbits the Sun at the second Lagrange point, L2, a point of equilibrium with Earth, ensuring a steadfast and unbroken view of the universe. While looking into the far-off parts of space, it not only explores light years but also involves a kind of time travel. The JWST uses instruments that detect infrared light from things and events dating back billions of years. As a result of the expanding universe, this light moves through a redshift, from the visible to the infrared frequency range. Luckily, the JWST can identify this infrared light radiated by heavenly bodies far away, enabling researchers to investigate the birth of stars, the development of galaxies, and the atmospheres of exoplanets. Its most recent historical discovery involves identifying an incomprehensible mass of cosmic systems at the edge of the observable universe. This finding casts doubt on the veracity of our current understanding of cosmic formation, provoking a reassessment of key cosmological assumptions. To comprehend how we arrived at this point, we should take a short excursion through the history of space exploration. Ancient cultures like the Greeks and Chinese laid the foundation for celestial understanding by observing divine bodies. Regulations devised by Newton in the 17th century provided a theoretical framework for space. In the mid-20th century, Edwin Hubble, an influential astronomer, made historic revelations that transformed space observational research. His observations revealed that far-off nebulae were actually distant, isolated galaxies outside the Milky Way, changing our understanding of the universe's scale and expansion. He demonstrated what became known as Hubble's law. Galaxies farther away were moving away at higher velocities, providing evidence for the post-World War II concept of an expanding universe. Space exploration marked history with the launch of Sputnik, the first artificial satellite, by the Soviet Union in 1957. Yuri Gagarin's orbital flight in 1961 and the Apollo 11 moon landing in 1969 were also monumental achievements. In 1990, the Hubble Space Telescope was launched, offering exceptional clarity and stunning insights into the universe. This marked the transition from earlier observations to the technological wonders represented by the James Webb Space Telescope. The Hubble telescope took the famous image of the Pillars of Creation in the Eagle Nebula, a stellar nursery formed by enormous columns of gas and dust. Another remarkable achievement was the Hubble Deep Field Image, showing a vast number of galaxies in what appeared to be an empty patch of sky. The HST also examined exoplanet atmospheres, identifying organic molecules and water-based compounds, alluding to the possibility of habitable zones beyond our solar system. It followed the development of the nearest observed supernova, SN 1987A, shedding light on the life cycle of massive stars. These achievements cemented the Hubble Space Telescope's legacy as a foundation of modern cosmology. To build upon this legacy, the James Webb Space Telescope was launched, incorporating technological advances and lessons from Hubble. Our current model of the universe's origins is explained by the prevailing Big Bang theory. The universe began about 13.8 billion years ago as a hot, dense singularity, quickly expanding and giving rise to energy, matter, and fundamental forces. As the universe cooled, atoms, stars, galaxies, and the structures we observe today formed. The Big Bang theory also explains cosmic microwave background radiation, the abundance of light elements, and the large-scale structure of the universe. Despite its wide acceptance, the Big Bang theory faced doubts. Alternative models like the steady-state theory proposed a universe without a beginning. However, most objections were resolved over time, especially with the detection of cosmic microwave background radiation in 1965, confirming Big Bang predictions. Space missions like WMAP and COBE, alongside improved technology, further validated the theory with accurate measurements of the cosmic microwave background radiation. Enter the JWST. Equipped with advanced infrared instruments that can peer through cosmic dust, it captures the universe's oldest light and observes objects formed shortly after the Big Bang. Its infrared capabilities allow it to focus on stellar nurseries and star-forming regions hidden from optical telescopes. Longer wavelength infrared light can penetrate interstellar dust, overcoming a limitation of the Hubble Space Telescope. The JWST can observe cooler objects, like exoplanets, brown dwarfs, and distant celestial bodies, that emit mostly in infrared. As celestial bodies move away, their emitted light stretches, creating a redshift. The JWST's ability to recognize these redshifted signals lets it capture light from the early universe, giving us data on cosmic formation and evolution. Energetic events like merging black holes or starbirths release primarily infrared radiation, further expanding JWST's reach. The telescope supplements optical telescopes like Hubble with its enhanced sensitivity and infrared detection capabilities. It allows us to peer deeper into space and uncover the hidden history of astronomy, revealing secrets and offering a more complete view of the universe's evolution. Recently, the JWST uncovered something so profound that it may lead to a re-examination of our entire cosmological simulation. It discovered massive galaxy clusters near the edge of the observable universe, formed just a few 100 million years after the Big Bang, during the cosmic dawn. The fact that such massive structures formed so early in the universe's history is both astonishing and challenging. These newly discovered galaxies, dense, ancient, and unexpectedly mature, pose a serious challenge to our current cosmological models. According to prevailing theories, galaxies of this size and complexity should not have had enough time to form so early in the universe's history. Yet, the JWST reveals their presence just a few 100 million years after the Big Bang, during what scientists call the cosmic dawn. This raises a fundamental question. Are our assumptions about cosmic evolution incomplete, or perhaps even flawed? The implications of these findings are profound. They may require a reworking of timelines, a deeper understanding of dark matter, or even a reconsideration of the very physics that govern how matter clumps together to form stars and galaxies. One possible explanation is that early galaxy formation was far more efficient than we thought. Perhaps the first stars were massive and short-lived, creating heavy elements rapidly and seeding their surroundings with the material needed for galaxy building blocks. Alternatively, there might be entirely new physics at play, phenomena we've yet to understand. Beyond galaxies, the JWST is also offering new insight into exoplanets, planets outside our solar system. With its ability to analyze the chemical composition of distant atmospheres, it's identifying signatures of water, carbon-based molecules, and other potential indicators of habitability. This opens up the thrilling possibility of eventually detecting signs of life beyond Earth. Instruments like NIRCam and MIRI aboard the JWST allow scientists to measure temperature, atmosphere, and weather patterns on distant worlds. For the first time, we can not only detect an exoplanet's presence but begin to understand what it's like to be there. And as we look further back, we also look further inward, toward the story of how everything began and where it may be headed. The telescope is not just a scientific instrument. It's a time machine, a mirror reflecting our endless curiosity, and a reminder of how much we still have to learn. Every image it sends back is a window into a time when the universe was young, chaotic, and full of possibility. As researchers sift through its vast and growing library of data, theories will evolve. Some will be confirmed. Others will fall away. But what remains constant is the spirit of exploration, an unyielding desire to understand the cosmos, from its first spark to its farthest horizon. In the end, the James Webb Space Telescope is more than a marvel of engineering. It is a symbol of humanity's reach, our ability to build tools that extend our senses across unimaginable distances and epochs. It challenges us not only to ask how the universe began, but to reflect on our place within it. And in doing so, it reminds us that even in the vast silence of space, we are not lost. We are learning. We are listening. We are looking forward. The discovery might cause us to reevaluate how we perceive the formation and early evolution of galaxies. The universe, as seen through early galaxies, is essential for deciphering the mysteries of cosmic origins. The JWST can gain insights into how stars and galaxies, and, over time, planetary systems, developed and changed. These observations span billions of years and also contribute to broader inquiries regarding the fundamental character of the universe, including its elements, structure, and the forces that govern its evolution. The Hubble Space Telescope was revolutionary, but it had limitations in observing the early universe. Its main restriction was its inability to effectively penetrate cosmic dust and detect the infrared light from ancient galaxies. These older telescopes relied on visible and ultraviolet light observations, which made it difficult to explore the early universe, as interstellar gas and dust absorb or distort these wavelengths. The James Webb Space Telescope represents a significant leap forward in observing galaxies from the universe's infancy. Unlike its predecessors, the JWST can observe celestial objects that formed within a few 100 million years after the Big Bang. Its sensitivity to infrared light and advanced imaging capabilities have uncovered a wealth of ancient galaxies with extraordinary clarity, deepening our understanding of the universe's evolutionary history. Preliminary findings have sparked waves across established cosmological models. The in-depth data presents aspects of the universe that challenge current theories, causing cosmologists to rethink the fundamental principles guiding our comprehension of cosmic evolution and structure. Discrepancies between observed data and theoretical predictions have ignited debates within the scientific community. Observations have revealed a greater number of galaxies in the early universe than anticipated by existing models, suggesting a faster and more complex evolutionary process. Some observed early galaxies appear more developed than expected, challenging conventional models that predict slower development. The discovery of massive, structured galaxies poses a challenge to existing hypotheses. Their distribution and arrangement suggest a more intricate and denser cosmos than previously considered. These observations raise fascinating questions and open new avenues for investigating cosmic structure formation. Early models are being challenged by the detection of large structures, prompting scientists to revise their models for a better understanding of how such vast structures could have formed rapidly after the Big Bang. A maze of unexplained phenomena is emerging, demanding explanations that may not contradict basic cosmological principles but do reveal significant disparities between predictions and early universe conditions. These differences may point to previously unknown processes, unexpected circumstances, or unidentified cosmic phenomena. In simple terms, scientists have responded by reconsidering and enhancing our models of the universe. At present, all we can say is that further exploration is required to integrate these unexpected observations into a more comprehensive understanding of the universe. Observations often provide exciting glimpses into the cosmos, but deeper investigations sometimes reveal unexpected details. Early observations might show specific arrangements or properties within distant galaxies, but closer examination can reveal differences in structure, composition, or evolutionary pathways. In conclusion, large-scale phenomena are extremely complex and require careful investigation to ensure accurate understanding. One example of a valuable investigative method is spectroscopy, which helps unravel the properties and history of celestial objects. By analyzing the light emitted or absorbed by these objects, spectroscopy provides detailed information about their chemical composition, temperature, density, and movement. This analysis aids in understanding the origins, development, and contributions of celestial bodies to the cosmic tapestry. The JWST has uncovered numerous cases where initial observations were later contradicted or refined. For instance, first glimpses of distant galaxies suggested simple structures dominated by light elements like hydrogen and helium, aligning with theoretical expectations. However, spectroscopic analysis with the JWST revealed fascinating variations, including the presence of heavier elements and compounds that were previously undetected or misunderstood. This defies conventional ideas about the chemical composition and mechanisms involved in the universe's early development. Initial assumptions about early galaxies were based on limited data, suggesting relatively uniform patterns of organization and development. But more detailed JWST investigations have revealed far greater variation, including intricate chemical compositions. The James Webb Space Telescope continues to redefine our understanding of the universe by shedding light on previously hidden regions. One of its most exciting capabilities is its ability to study exoplanets from space in unprecedented detail. By analyzing the atmospheres of planets orbiting distant stars, the JWST can identify important chemical signatures, such as water vapor, carbon dioxide, and organic compounds like methane. These findings offer valuable insight into the potential habitability of exoplanets and the conditions that might support life beyond Earth. In addition to exploring distant worlds, the JWST is transforming our understanding of star formation. It can observe stars forming in regions shrouded in dense gas and dust clouds that optical telescopes cannot penetrate. With its ability to detect infrared light, the JWST picks up the faintest traces of new stars emerging from darkness, offering a clearer picture of the processes that lead to star and planetary system formation. Astronomers are gaining deeper understanding of how stars like our Sun form and evolve over time. Another remarkable aspect of JWST's research is its ability to peer into the hearts of galaxies. Supermassive black holes are thought to reside at the center of most large galaxies. The JWST's advanced instruments allow scientists to observe how matter behaves around these black holes, offering fresh insights into their growth and influence on galactic evolution. The immense energy they release can shape entire galaxies, and JWST's findings are helping astronomers piece together the story of how galaxies and their central black holes co-evolve. JWST's discoveries not only answer long-standing questions but also raise new ones. As it explores the universe's past, it is revealing phenomena that challenge existing theories and models. These challenges drive the scientific community to refine current cosmological models and open up new avenues of research that were previously unimaginable. The discoveries made by the JWST are not only expanding the boundaries of our knowledge, but also helping reshape the fundamental principles by which we understand the universe itself.